Alright, we have 7 components in total, 4 microchips, 2 resistors, and 1 capacitor. We randomly select 3 components without replacement. We let X be the number of microchips selected and Y be the number of resistors selected. To find the joint probability, we count the number of ways to choose X microchips from 4, Y resistors from 2, and the remaining components from the capacitor, then divide by the total number of ways to choose 3 from 7. All valid combinations are shown in the joint probability table. The marginal distribution of X is found by adding across rows, and the marginal distribution of Y by adding down columns. To check for independence, we compare Px equals 1 and Y equals 1 with Px equals 1 times Py equals 1. As a result, we get that A over 35 is not equal to 48 over 245. So since these values are not equal, then we can say that S and Y are not independent. Next, we find the expected values of X and Y. The expected value is found by multiplying each value by its probability and adding them up. So for finding expected value of X, we can use the formula as shown in the image, which is the summation of all X times gx, and then as a result we'll get 12 over 7. And as for expected value of Y, we do the same as expected value of X, but this time we use the formula of summation of all Y's times hy, and then as a result we'll get ey equals 6 over 7. The joint probability distribution of discrete random variables x and y is given in the following table. So first we need to find the marginal distributions of x and y. To find the marginal distribution of x, we add the probabilities down each column. Px equals 1 gives 0.43 and Px equals 2 gives 0.57. Now to find the marginal distribution of y, we add across each row of values of y. So py equals 1 gives 0.39, py equals 2 gives 0.35, and py equals 3 gives 0.26. So since x can only be 1 or 2, x is bigger or equal to means x is equal to 2. By solving it, we get that p of x is bigger or equal to 2 given y equals 2 is 22 over 35. Next, the question asks to calculate the covariance of x and y. Like I said before, to find the expected value, we need to find all the summation of a variable multiplied by its probability. So to find the expected value of x, we need to find the summation of all x's and multiply by its probability, which gives us 1.57. And then we do the same for ey, so we'll get 1.87. But to find the expected value of combination of x multiplied by y, we need to use the marginal distribution combination of x and y by adding up all x's and all y's in the product of x and y. So by doing this, we'll get 2.88. And then we have to find covariance. So the formula is shown in the image, which is E x multiplied by y and then minus EX times EY. So by substitute in these expected values, so we'll get 2.88 minus 1.57 times 1.87, so which results that we'll get negative 0.0559.
Okay, for question 2a, first Roman is to find the marginal density of x and y. So we will start it with the marginal density of x or gx. To find it, we need to integrate the equation with respect to y and then get the answer down below, which is 1 over 60 8x plus 8. To get to as for the marginal density of y or hy is pretty much the same, but we now must integrate it with respect to x, which the answer is 1 over 60 y plus 3y. So for the second Roman is to find x plus y is less than equal to 2. So we first need to find the exact limit for integration, which can be shown from the graph, and then we choose to what to integrate first, which in my case is dy dx. As we have determined the limit earlier, now we can insert the upper limit of y is x minus 2. After the double integration, the final answer will be 1 over 15.
For question 2b, we are given a joint probability density function of two continuous random variables x and y. The joint PDF is fxy equals to 8xy for 0 less than or equal to y less than or equal to x and less than or equal to 1 and 0 elsewhere. The objective of this question are to find the expected values of x, y, and xy, and then calculate the covariance to determine whether x and y are independent. This graph, y equal x, shows the possibilities of the values of x and y because the region of the joint PDF is defined by 0 less than or equal to y less than or equal to x and less than or equal to 1. To find the expected value of x, we use the formula Ex equals to double integral x times fxy dy dx, because Ex represents the average or mean value of x weighted by its probability over all possible values. We integrate with respect to y first from 0 to x, then with respect to x from 0 to 1 because the region of the joint PDF is defined by 0 equals to or less than y less than or equals to x and less than or equals to 1, which mean that the range of y is 0 to x and the range of x is 0 to 1. After evaluating the integrals, we find that Ex is equals to 4 over 5. Similarly, for y, the expected value is Ey equals to double integral y fxy dy dx. Again, we integrate over the same triangular region because y can only take values from 0 to x. This gives Ey equals to 8 over 15. The smaller value of Ey compared to Ex makes sense because y is always less than or equal to x in the defined region. Next, the expected value of the product xy is calculated using Exy equals to double integral xy times fxy dy dx. This measures the average product of x and y, taking into account how often combination of x and y occur in the defined region. After integration, we will get Exy equals to 4 over 9. Covariance measures how x and y vary together. It is calculated as cov xy equals to Exy minus Ex times Ey. Substituting our values, cov xy is equals to 4 over 9 minus 4 over 5 times 8 over 15, which is equal to 4 over 225. The positive covariance indicates a slight tendency for x and y to increase together. X and y are not independent because if they were, both x and y would be equal to 0, which is it is not.